When writing software, programmers operate under a convenient assumption. They have access to an infinite, unbroken, expansive memory, starting cleanly at address 0. The physical hardware dictates a different reality. Main memory, or RAM, is strictly finite. It is highly fragmented and fiercely contested by dozens of active programs at any given moment. If every program actually required a single contiguous block of physical memory to execute, the system would immediately hit a bottleneck. Concurrency would grind to a halt the moment a few large applications launched. To bypass this physical limitation, the operating system abandons contiguous physical allocation entirely. Instead, it relies on a virtualized logistical grid to manage data. This grid divides into 3 domains: virtual storage, central storage, and auxiliary storage. z/OS manages data across these planes using strict 4 kilobyte blocks. It links domains using dynamic address translation and moves data using 2 processes, paging and swapping. By abstracting the physical hardware into this logistical system, an enterprise server can run massive, competing workloads concurrently without exhausting its physical resources. To standardize management across the entire system, the operating system chops all memory into identical blocks, exactly 4,096 bytes, or 4 kilobytes, in size. The terminology for these blocks changes when that same 4 kilobyte block physically loads into main memory, central storage. It is called a frame. And when the block is written out to a physical disk device, or auxiliary storage, it is called a slot. This diagram maps the domains. The gray virtual memory column holds pages A through F. Active pages must reside in green real memory frames. Inactive pages are evicted to orange auxiliary slots. Though contiguous virtually, physically these blocks are completely fractured and scattered. Because a page, a frame, and a slot share the exact same 4 kilobyte footprint, the operating system can swap them one-to-one. This strict uniformity eliminates external physical fragmentation, regardless of how scattered the data becomes. If the virtual pages of a program are scattered randomly across physical frames, the processor faces a logistical hurdle. How does it locate a specific piece of data fast enough to execute an instruction? The solution is a hardware-level linkage system called Dynamic Address Translation, or DAT. This diagram maps the DAT process. The hardware expands the virtual address to 64 bits. First, the segment index locates an entry in the blue segment table. This points to the green page table, where the page index isolates the physical frame's real address. Finally, it adds the byte index. This acts as a displacement value, pinpointing the exact piece of data within that specific 4,096 byte frame. This multi-step lookup happens instantly at the hardware level for every single instruction the CPU processes, operating at lightning speed. DAT acts as an invisible tether. It maintains the programmer's assumption of contiguous memory, giving the operating system the freedom to physically scatter data for maximum efficiency. The translation process runs smoothly as long as the data is actually in RAM. But occasionally, the DAT hardware checks a page table entry and finds an invalid bit turned on. This invalid bit indicates that the required page is not in central storage. It is currently resting on disk in an auxiliary slot. Finding this triggers a hardware interrupt, known as a page fault. The operating system responds immediately by executing a page in. It copies the data from the auxiliary slot back into an available central frame, turning the invalid bit off. But this process assumes there is an available frame. If the system's RAM is completely full, a page-in cannot occur until the OS creates space. It does this through a process called page stealing. The system applies a least-used algorithm to identify an inactive frame that is taking up valuable real estate. Once identified, the OS performs a page out. It copies that inactive frame's contents to an auxiliary slot, invalidates the old page table entry, and frees the frame up for the incoming data. Paging is a highly granular micromanagement system. It surgically swaps 4 kilobyte blocks back and forth to keep only the most actively used data in expensive physical memory. Paging handles the standard flow of data, but when a system becomes critically saturated, shifting 4 kilobyte blocks is not enough to save it. To resolve these severe system-wide resource bottlenecks, the operating system deploys a macro-level intervention tool known as swapping. Swapping is the transfer of an entire address space. Every single page of a program is forcefully moved between central and auxiliary storage at once. The trigger mechanism is entirely different. While paging is a reactive response to a hardware fault, swapping is directed by the System Resource Manager, or SRM, based on systemic health. The SRM dictates a swap out when there is a severe shortage of slottage or central frames, or to aggressively balance the current mix of running programs. It also acts on wait states. If a time-sharing user is sitting idle, waiting to input a terminal command, their program is hogging RAM without doing any productive work. The SRM detects this and swaps the address space to disk. A swapped-out address space is completely inactive. It resides strictly on disk and cannot run until the SRM decides conditions have improved enough to swap it back in. Swapping acts as the system's emergency pressure valve. By clearing massive quantities of RAM in a single operation, it prevents total system gridlock. These two memory management methods operate on different scales. Paging is a micro-operation, managing memory block by block with strict 4 kilobyte granularity, driven entirely by page faults. Swapping is a macro-operation, managing over-allocation with address space granularity, driven by system shortages to move entire processes at once. They work in symbiosis. Paging handles the daily logistical traffic, while swapping manages the overall zoning of the system. Together, the 4 kilobyte triad, the DAT hardware, and the dual logistics of paging and swapping abstract the limits of physical hardware. This enables z/OS to maintain high concurrency and process massive workloads, turning finite RAM into an engine for continuous execution.